Ahora sí. Le bajo.
Aquí tienen que llenar todo.
Everybody, ok.
Aquí y acá.
A la orden.
El que no llena paga y el que llena es gratis.
Hello.
Oh,
How are you?
I'm well. How are you?
Fine.
Good to see you.
Yeah, me too.
I'm well.
Hay que llenar aquí.
This room is new.
It's renewed. Yeah, it was we prepared it for teleconference and it's nice.
This was half the size now.
It's was different. I think it was the same shape, but with chairs facing these individual chairs. It was like any regular.
Yeah. Yeah.
Is that you?
200 years ago.
I noticed it for the picture. The picture is old.
Yeah.
Not you. The picture. ¿Iniciaste la transmisión nomás por si acaso para que la gente se vaya conectando?
Sí, ya está listo. Por eso fue lo que sonó, se escuchó
Ah,
ahí.
ok.
Estaba probando que se escuchara bien, no sé qué.
Claro. ¿Verdad que no está aquí?
Podemos dejar eso ahí. El micrófono para
Yo
el
pedí
inicio.
que cambiaran eso, está todo mal escrito.
¿Qué es esa el root de la
87 912 900. No haya un. Hola, ¿cómo te llamas?
¿Dónde lo dejo, Sergio?
Abajo no va a continuar. Es que hay que llenar las dos partes.
Ah, ya. Sergio, a la tarde tenía un ratito o va a estar
Yo tengo.
Morning.
Good morning. How are you?
Claro, entonces, perdona, era porque con eso nada. El que te escuché llamando por. Sí, ya. Te escuché que estaba llamando por otro lado.
¿Cómo estás? Qué gusto verla. Bien.
Muy bien, me tenía a las 5.
Yo creo que la idea es clara. Ah, qué es lo que queremos y qué es lo que necesitamos. ¿Vos vas a preguntar? No te voy a ver. Mira, tienes que llenar dos cositas, esta o una hoja de esta y la lista de asistencia, por favor. So, no, 9 a.m. Chilean time, maybe 9:15.
9:15, yes.
No,
Yeah.
you are used to this, huh?
We called it baker's time.
Ah.
Superior.
¿Qué le va a presentar?
Sí.
Para que pueda ocupar ese micrófono.
Ya.
Lo enciende y
Okay.
y después ese mismo micrófono lo ocupamos para las preguntas.
Ya.
Sí, aquí no te lo digo. No, eso es aparte ya. Es el 87 912 900 que llegó.
Is there going to be a coffee break?
Yes.
At what time?
It's ready already.
Oh, let's have it now.
Yeah. So you decide.
Okay, and we go until 1, 2,
One.
1. Okay.
One is fine. Also, you decide. You want
Yeah.
to skip, stop a little earlier or continue on. It's open.
Okay.
I'm gonna explain that to them.
Yeah.
I'm gonna explain that we squeezed into 2 days.
Yep.
Así que le voy a insistir hoy día. Que eran 4 o 5 personas. Pero tenemos que ubicarle
Y la lista de asistencia. Las dos cosas. Ah, ya te leí. Bueno, buenos días. Es para nosotros, digamos, un honor, una alegría tremenda de poder tener con David nuevamente y celebrar, yo creo que ya más de 25 años de una larga amistad y colaboración con lo que fue inicialmente la Unidad de Epidemiología Clínica y posteriormente el SIGE. Yo creo que no necesita mayores presentaciones, yo creo que todos ustedes han visto su currículum, es donde está ahí en la página web, ¿cierto? Así que, David, sin más que agradecerte, todo tuyo, ¿no? Sí me gustaría primero si ustedes se quieren presentar. David entiende español si le hablamos lento, right? Right? Pero no habla español, ¿no? Otro aspecto importante de ¿cómo se llama? Del curso es que estuvimos revisando los materiales que él va a presentar y realmente con 2 días va a ser suficiente, ¿no? Entonces va a ser hoy día de 9 hasta la 1 más o menos y mañana también de 9 a 1. Eso en la parte de cómo va a ocurrir el curso. Él va a hablar en inglés. Si ustedes tienen dudas, levantan la mano para poder aclarar las dudas que eventualmente puedan tener. Josiana y yo vamos a estar atentos, digamos, a traducción en caso que sea necesario de algunos elementos. Creo que eso es la parte de comerciales, ¿no? Entonces, si se quieren presentar.
Bueno, Gladys Morales, mucho gusto. Soy nutricionista, máster en promoción de la salud, doctora en salud pública y trabajo en el departamento de salud pública de acá de la Universidad de la Frontera.
Hola.
Hola.
Hola también a todo el resto. Luis Bustos, bioestadístico. Pertenezco también al Departamento de Salud Pública y al SIGES. Y un gusto de estar con todos ustedes.
Good morning. I'm Josiana Robinovich. I'm physiotherapist and I belong to the Public Health Department. I also studied Master in Public Health and finishing my PhD, also in the same subject.
Hola, Federico, médico del hospital y estoy alumno de primer año de epidemiología clínica.
Hola, buenos días. Me llamo Tania Flores y soy docente de la Facultad de Odontología de la UFRO, magíster en ciencias odontológicas.
Hola, mi nombre es Luis Cepeda, soy fonoaudiólogo y estudiante de primer año de magíster de epidemiología clínica.
Bueno, mi nombre es Richard Jiménez, soy informático del SIGES y bueno, estamos con el equipo de multimedia aquí para colaborarles en la transmisión en vivo de la clase.
Mauro y Alexander.
Mi nombre es Mauro, yo estoy a cargo de la transmisión en vivo.
Okay, David.
Okay, thank you. I am delighted to be back here after many years with good friends. The only problem is that I was told I was being invited here because of my expertise in structural equation modeling and item response theory, but when I get here, this is what Sergio has me doing. But it did taste very good.
Yeah, he did a good job, actually.
So, let's discuss how we get to structural equation modeling. At the simplest level, we have just bivariate correlation, where we could look at only 2 variables at a time. We move up in the world a little bit and we have multiple correlation, where we have more than two independent variables, but we have a problem in that a variable is either a dependent variable or an independent variable. This is solved when we get to path analysis, where a variable could be a dependent variable in one situation and then become an independent variable along a pathway of causation. The difficulty with path analysis is that it deals only with measured variables, that is, variables that we could measure with a scale, a ruler, observation, or whatever. And the next step in evolution is structural equation modeling.
Yes, sir. ¿Alguna pregunta ahí?
No. Stop me at any time if you have questions. The major difference between path analysis and structural equation modeling, as I said, is that path analysis is limited to measured variables, and structural equation modeling can handle both measured and latent variables. By the way, I could leave copies of the talk, so you don't have to take notes. So what's a measured variable? A measured variable is one that's observed directly. This is what we are most used to. Paper and pencil tests, physical measurements, and so on. A latent variable has many different names. In personality theory, we call them constructs. In factor analysis, we call them factors, but they're all the same thing. We do not see a latent variable. What we see are correlations among measured variables, and we assume that the correlations are due to the fact that they are all the outward manifestations of the latent variable. So using the notation of structural equation modeling, we have a latent variable, and latent variables are always drawn with an oval. So we have a latent variable of intelligence, which we don't see. Some people say we don't see intelligence because it's in such limited supply, as we saw with the elections. And because of the influence of this unseen latent variable, what we do see are measured variables. We see the size, we can measure the size of someone's vocabulary. We can measure problem solving. We can measure math skills. And we say that all of these are correlated because they are all due to the underlying factor, the underlying construct, the underlying latent variable of intelligence. Okay? So these are the measured variables, which we denote with a square or rectangle, and that's the latent variable. If we do an exploratory factor analysis on this model, this is what we would come up with. We have this, which in factor analysis is called factor loadings. In path analysis, structural equation modeling, we call them path coefficients. Same thing. Factor loadings, path coefficients. And then we get another term called uniqueness. That is, what is vocabulary measuring that is not measured by problem solving? So most of vocabulary is due to intelligence. But even though all three are due to intelligence, each of them has a component that's unique to itself. And in factor analysis terms, that's called uniqueness. Whenever we do factor analysis, structural equation modeling, whatever, we always start off with a correlation matrix. And in a correlation matrix, we standardize the variables so that they have a variance of 1. So each variable has the variance of 1. So the path coefficient squared plus the uniqueness squared is equal to 1 for all of these variables. So what we've done is taken the variance of that variable and decomposed it into that part due to the latent construct and what's unique. Okay? This is what we see in factor analysis all the time. And the correlation between the measured variables is just the product of the path coefficients. Clear so far?
Pregunta?
No. Okay. What is the advantage of a latent variable? One advantage is that we can take a number of measured variables, each of which is somewhat unreliable, combine them into a scale. Even though each of the measured variables is a scale, we now combine them all into a superscale, and we can disattenuate the reliability. What does disattenuate mean? It means we can determine the correlation between the constructs as if there were no unreliability in the scales. That is, we could figure out what is the reliability, correct for it, as if the scales were perfectly reliable.
Can you expand a little bit more on that?
I'm glad you asked. Yes.
Okay, nice.
When we correlate two variables, it's affected by three things. How strong the relationship is between the variables, but then it's decreased, it's attenuated by the unreliability of the first scale and the unreliability of the second scale. So the lower the reliabilities, the lower the calculated correlation between the two variables. So it's possible that if, for example, we were looking at the reliability or the correlation between vocabulary and problem solving, we know in theory the correlation should be very high. But if we correlate two scales, it will be lower because the scales that I'm using to measure vocabulary and problem solving are unreliable. And if I am developing a theory of intelligence, I don't want to know the calculated correlation. I want to know the theoretical correlation between the variables. Is that clear? Yes, yes, please. Do we need the microphone? Yeah, because, no, it's being recorded. And
you expand a little about the theoretical correlation? Because how can we know that? I mean, we know the measures because they are done with some scale. But what do you mean by theoretical correlation? Sorry, ¿ayer? ¿De nuevo? I would like to know what is the meaning exactly of theoretical correlation in opposed to...
Let me give an example and see if that helps. Let's assume we want to look at the theoretical relationship between anxiety and introversion. Okay? So we take two tests of anxiety, A1 and A2, and two tests of introversion, and let's give them to 200 people. So what I would get is a correlation matrix. The correlation between A1 and A2 and between I1 and I2 is the same as parallel form reliability. Two different measures of the same construct. Clear? And the other correlations are the calculated correlations among the scales. Between the first anxiety scale and the first introversion scale, the first anxiety scale and the second introversion scale, and so on. So I would conclude that the calculated correlation between introversion and anxiety is somewhere between 0.40, 0.48. Now let's use structural equation modeling. I derive two latent constructs of anxiety and introversion, and each latent construct is measured with two scales. And now if I look at the correlation between the latent constructs, I get a much higher correlation, from 0.4 or 0.5 up to 0.6, which means that anxiety and introversion are correlated in theory about 0.6, but the measured correlation, looking at only one scale at a time, is about 0.4. So is that clear?
So how did you get the 0.62 correlation?
By using structural equation modeling. Well, that's the correlation. I could do the whole thing by hand and figure out the disattenuated correlation, but in structural equation modeling, what I've done is create two superscales, and we'll see later how we do that. So I've created a superscale of anxiety, which is made up of two measured scales of anxiety, and a superscale of introversion made up of two measured variables of introversion. And now I correlate the latent variables. Okay? Okay. When we get into path analysis and structural equation modeling, we have to learn a few more terms. And two of the terms are an exogenous variable, exogenous meaning outside, and in structural equation drawings in the notation, exogenous variables have arrows coming from them. That is, we are measuring the influence that exogenous variables have on our model, but there are no arrows pointing to them. We're not measuring them. We know something influences them, but we're not measuring whatever it is that's influencing the variable. Endogenous variables have at least one straight arrow, and we'll see why I emphasize straight, one straight arrow pointing to them. Something in our model is influencing the endogenous variable. Why the change in terms? Why don't we continue to use dependent and independent variable? Well, let's take a path analysis model like this, where we have well-being, and well-being, we say, is influenced by symptoms, wealth, and IQ. Each of them have a path to well-being. However, wealth is also influenced by IQ. So IQ has a direct effect on well-being, and it has an effect on well-being mediated by wealth. So it's obvious that well-being is a dependent variable, no question. It's obvious that symptoms and IQ are independent variables, no question. What do we call wealth? Is it a dependent variable or an independent variable? And the answer is yes. It's a dependent variable insofar as IQ is concerned. It's an independent variable insofar as well-being is concerned. So it's serving both roles because it's on a pathway. So independent and dependent don't apply here. So what we say is symptoms and IQ are exogenous variables because they only have straight arrows coming from them. Okay?
To well-being.
To well-being. And IQ also has a straight arrow to wealth. Yep. And in this model, wealth and well-being are endogenous variables because they have straight arrows pointing to them. And the curved arrow with an arrowhead at both ends means a covariation, correlation. Is this clear so far? Any questions? Okay. In path analysis and in structural equation modeling, exogenous variables do not have error terms. We're assuming, as in regression. Don't forget, in regression, one of the assumptions is that the independent variables are measured without error. It's a ridiculous assumption, but it's one of the assumptions. This is simply an extension of multiple regression. So it's assuming that exogenous variables do not have error. And if they did have error, we can't measure it anyway. Endogenous variables always have an error term, except in structural equation modeling we don't call it an error term. we call it a disturbance term. Why? Just to confuse you. We have many terms like this designed just to confuse you. So, well-being has to have an error term. It's an endogenous variable. If we use computer program to do structural equation, not if, when we do it, we can't do it by hand. When we use a program, most programs automatically attach a disturbance or an error term. Some programs label it as an E, some label it as a D. In Stata, if the variable is called y1, Stata automatically assigns an error term E.y1. We don't have to do it. It's done automatically. And it's assumed that the error terms are uncorrelated. We can override this, and there are times when we do, but the starting assumption is that the errors are uncorrelated. Okay so far? So, there are 5 steps in structural equation modeling. Specifying the model, identifying the model, estimating the model, testing how good the fit is, and then starting again, re-specifying the model and trying it again. Yes?
Thank you. With relation to the errors that are uncorrelated, does this have something to do with the construction of the model? Because at the beginning, with theoretical background, we build a model. So shall we check for this when we theoretically build the model?
No.
I really don't understand very well what do you mean with the errors uncorrelated.
This is an assumption that we make with most statistical tests. In a regression, for example, if we have 5 predictive variables, we assume that the errors of each of the 5 predictive variables are independent from one another. That each variable has some error, but it's not correlated with the error of another variable.
Mm-hmm.
Okay? This is saying exactly the same thing.
Even though you are trying to build a superscale, let's say test anxiety 1 and anxiety 2, they cannot, their respective errors are not correlated. We assume that they are not.
That's right. We assume that the scales are correlated, but not the errors.
Okay, now I get it.
Okay?
Mm-hmm.
Let's go back a little bit. Try to think. Okay, in measurement theory, have people studied measurement theory, scale development?
Most of them.
Most of them. Okay. Remember that in scale development, or in measurement theory, we say that an observed score, a score that we get on a test, or a score that we get when we stand somebody on a scale, or take their blood pressure, we have an observed score. That score is influenced by error. So the observed score is equal to a true score, which we never see, plus error. Sometimes the error will increase the score, sometimes the error will decrease the score. Overall, over an infinite number of measurements, the error will have a mean of 0 and some standard deviation. And the errors across scales are uncorrelated. Okay, so that's all this is saying. We'll see later we could override this. We could say in some situations the errors may be correlated, and we'll see why. Okay? There are actually two parts in specifying the model. What we call the measurement model and the structural model. The measurement model defines the relationships between the measured variables and the latent trait. It's a confirmatory factor analysis. The structural model is the second step, and it looks at the relationship among the latent variables.
If more than one.
If more than one, that's right. If it's only one, then it's a confirmatory factor analysis. And there are a few different ways that people do it. There's a one-step approach where you specify the measurement model and the structural model at the same time, run everything all at once. Very possible, and there's a lot to understand. So many people use a two-step approach. First we do the measurement model. If the measurement model is good, then we go to the structural model. Yes?
Can you repeat again, please, the difference between measurement model and structural model?
Mm-hmm. The measurement model looks at the relationship among the measured variables and whether or not they can be put together to constitute a latent variable.
Just one factor.
Just one at a time, that's right. Once we've developed one or more latent variables, then we look at, is there a relationship among the latent variables? And we'll see this in a few minutes.
Es súper importante eso, no sé si todos les queda claro la diferencia, o lo explico en español, ¿sí? ¿O no? ¿Sí? Claro, cuando tú tienes una escala con un solo dominio, entonces él habla del modelo de medición. Pero cuando tú tienes una escala que tiene dos o más dominios, entonces él habla del modelo estructural. Esencialmente, en términos sencillos, la diferencia, ¿no? Okay.
So, as I said, we can stipulate, we can draw the measurement model and the structural model and analyze them in one step. Or we could first try to determine the measurement model, and then if that works, or after we have to modify it, then we do a structural model. That's assuming we have a good model. Sometimes we don't. So sometimes we start off with an exploratory factor analysis, follow that with a confirmatory factor analysis, then do structural equation modeling, and try different structural equation models. But the two-step approach is the most widely used. First, develop a measurement model or models, and then put those together into a structural model. Let's take a look at an example. So here we have a more complicated model. We've defined a latent variable of symptoms made up of 3 variables, measured variables, a latent variable of wealth made up of 3 measured variables, a latent variable of intelligence, a latent variable of well-being made up of 2. Okay? These all have 3. Why 3? Because I got lazy. It was easy to draw one and then just copy it. Doesn't have to have the same number in real life. So that's a measurement model. That's saying, how good is my latent variable of symptoms? Am I measuring it well with these 3 scales? And that's a second measurement model, and a third measurement model, and a fourth measurement model. Once I am satisfied that these measurement models are all good, then I could put them into a structural model where I'm looking at the relationship among the latent variables. Questions?
And do you take into account the relationship between IQ and wealth somehow, or this is not including that?
No, no. This is assuming those are independent latent variables.
So there's no way to account for confusion?
We can, but it makes the model much more difficult to interpret.
But it can be done.
Yes, but also don't forget we could look at the correlation between variables by multiplying their path coefficient. Remember, so we could do it.
So let's say if you want to take into account how much IQ is related to wealth, whether for stocks, income, or savings, then you can determine that before, because it will influence the outcome at the end.
We can look at the correlation between IQ and wealth because if you remember, if we correlate the path coefficients, that gives us the correlation.
And it that's affect the outcome. Okay.
Yeah.
Thank you.
Other questions? Okay. So, the questions that we ask in this first step. How well do the measured variables reflect the latent variable? Second question. Are some of the observed variables better than other observed variables? How reliable is each measured variable? And then finally, how good is the structural model? Okay? Identification. This assumes I gave the path analysis talk first. The number of parameters has to be less than the number of observations. The number of observations has nothing to do with the sample size. It has to do with the number of measured variables. Okay? The number of observations is the number of measured variables times the number of measured variables plus 1 divided by 2. The number of parameters we'll see in a minute. That gets complicated. And the other thing that we have to worry about is that the rank of a matrix cannot be less than the number of variables in the matrix. You're all very comfortable with matrix algebra? No. So let's discuss it.
Okay, yeah, okay.
The rank of a matrix is the number of independent rows and columns. So look at that matrix, a simple 2 by 2 matrix. Row 2 is simply row 1 times 2. So this row is simply twice that row. So the 2 rows are not independent. 1 row is perfectly predictable by another row. When does this happen? Are people familiar with the Wechsler intelligence scales? No? Okay. The Wechsler intelligence scales are different ones for different age groups. And they consist of 2 major parts. There's a verbal intelligence and a performance or a nonverbal intelligence. The verbal intelligence part itself has a number of subscales, measuring somebody's vocabulary, somebody's arithmetic skills, somebody's problem-solving skills, information about the world, and so on. The performance part also has a number of subscales. It's called block design, so on. Let's say I give the test to a large number of people, and I enter scores for each of the subtests. Let's say there are 5, plus the verbal IQ. Each of the performance subtests, and again, let's assume there are 5, and the performance IQ and the total IQ. So I have entered 13 separate scores. Is that clear? 5 performance subtests, 5 verbal subtests, verbal IQ, performance IQ, total IQ. So now I have a matrix with 13 columns and as many rows as I have subjects. Are those columns independent from one another? The answer is no. Because if I add up the verbal subtests, I will perfectly predict the verbal IQ. If I add up the performance subtests, I will perfectly predict the performance IQ. If I add up the verbal IQ and the performance IQ, I will perfectly predict the total IQ. So even though I have 13 columns in the matrix, I only have 10 independent variables. So the rank of the matrix is less than 13. So if I try to analyze that with any multivariable technique, multiple regression, factor analysis, path analysis, structural equation modeling, whatever, I will have problems because the rank of the matrix is less than the number of columns. Is that clear?
Yep. Pregunta.
Okay. So, given these two limitations, that the number of parameters has to be less than the number of observations, and the rank of the matrix cannot be less than the number of variables, how do I accomplish that? How am I sure to limit the number of parameters I have? I have to estimate. And the solution is to constrain some variables. Let me explain. If I have the equation 5 equals b plus c, can I solve that? The answer is no. There are an infinite number of solutions. But I could set b equal to minus 8. If I set b equal to minus 8, what I've done is fix the level of b and say c is free. I'm going to estimate what c is. And I could solve the equation. So I have fixed one variable. So I've limited the number of parameters I have to estimate. Another way I could solve this is to say, I don't know what b is, but whatever it is, it's equal to c. And again, I've limited the number of parameters I have to estimate. I don't have to estimate b and c. I could just estimate one of them because I know the other one is equal. So again, I've limited the number of parameters I have to estimate. So in this case, what I've said is that b and c are constrained. Is that clear?
When do you do that? At model specification?
Yeah.
Okay.
Yeah. So we have three types of variables. Free variables, these are variables that could assume any value, and I'm using the statistics, the mathematics of structural equation modeling to estimate them. Or I can fix the value ahead of time, or I can constrain the variable. I can say, I don't know what it is. I can't fix it, but it has to be equal to another parameter. So, easiest way to constrain a variable, don't draw a path. So, there are three paths I haven't drawn. In other words, I've fixed those path coefficients to 0. Okay? Yes?
If you go back to the Josiana's example, go back, that way.
Okay.
Because she wanted to put some arrows between wealth and IQ. So
no, that's a different issue.
A different issue?
That's a different issue.
Oh, okay.
That's looking at relationships among latent variables.
Oh, I see. You're talking okay.
Yeah. Now, yes, I could draw an arrow, but that's different from a correlation.
Yeah. But you're adding a parameter anyway.
Yes. Yes. Another way I can constrain parameters is that for each error term, I'm estimating two things. I'm estimating the magnitude of the error, and I'm estimating the path coefficient. That's two parameters, and I can't estimate them both. One of them has to be fixed. I could fix either one. I could say I could fix the value of the variance, or I could fix the path coefficient. By default, we fix the path coefficient. That's less important to know. We say it's going to be 1, so I can estimate the error term. Another way I can limit the number of parameters that I have to do is that for each of the latent variables, I set one of the path coefficients to 1. If I don't do anything, if I don't tell the computer anything else, all of the computer programs will work the same way. They will fit the path of the first variable equal to 1. I can override it. If I know information about these variables, it's best to take the variable with the highest reliability and set that equal to 1. Does it matter? Not much. If we change which variable we set equal to 1, it will change the value of the unstandardized coefficients. But most of the time, we work with standardized coefficients. So in practice, it doesn't matter which one we set equal to 1. But we do have to set one of them equal to 1 in every model. And again, it's done automatically by the program. And does anybody use Stata?
Most of us.
Yeah. This is the command in Stata for changing. So if I didn't say anything, the path coefficient from the SCL90 would have been set equal to 1. If I say symptoms, that's the latent variable, arrow HS, that's the name of this variable, at 1, means I've changed which variable has a loading of 1. Yeah. Okay, so this is what I said. One path must be fixed. For the most part, the path doesn't matter. Use the variable with the highest reliability. And it will change the unstandardized coefficients, but not the standardized coefficients. Yes?
One part, please. Then, how do you interpret then the 1 there? When you run the program and so on and so forth, and you get the coefficient, all other coefficients, how is the interpretation?
It will still give us the information that we need, but it will tell us relative to this variable. But with the standardized coefficients, we'll get all of the information that we need. It won't print out a 1. It will print out the actual estimated coefficient. It's only the unstandardized coefficient where that will remain a 1.
I see.
Okay. Here's one situation where we do specify that the covariance or that the errors are correlated. I said before we assume that the errors are uncorrelated. But sometimes, in order to constrain the number of parameters, I could override that. Let's say Y1 and Y2 are the same test, one filled out by the mother, one filled out by the father. because they're the same test, I could assume that the variance of those tests is the same. I don't know what it is, but there's no reason to assume that the same scale filled out by the mother as by the father should have a different variance. So I could say, I'm setting the variance as equal to 0. Or maybe these are two different questionnaires or scales, but that's time 1 and that's time 2. And again, I could say it's fairly safe to assume that the variances are the same across times. So I don't know what they are, but I'm going to say they're equal. And that means there's one less parameter I have to estimate. Clear? Yes?
Sorry. Yeah, it's related to constraining variables. How much does it might affect the outcome? Because we are assuming lots of things. We are assuming that one path equals 1 and that variances are 0. So
that's 0. Equal.
Okay, that they are equal. So it's one assumption and then another. Are there any way to estimate that we assume too many things, or
no?
No?
No. I will stress this point over and over and over again in this talk. You're going to get tired of the talk. Structural equation modeling is not a theory building technique. It's a theory testing technique. The most important part is that we have to specify the model. We cannot rely on the statistics to tell us what's the correct model. Okay? So our assumptions may be wrong. Maybe those variances shouldn't be equal. Very often, when we leave out a path, we know we're making a mistake leaving out a path. For example, let's assume this is mother's anxiety, mother's depression, child's anxiety, child's depression. We are assuming that mother's anxiety affects the child's anxiety, and mother's anxiety affects the child's depression. We are assuming the mother's depression affects the child's depression, and the mother's depression does not affect the child's anxiety. That's probably wrong. We are also assuming that the child's anxiety and depression are not affecting the mother's anxiety and depression. And we know that's wrong. If my kid is anxious, I'm going to be anxious. If my kid is depressed, that's going to make me depressed. Let me just finish. And we're also assuming there's no relationship between anxiety and depression. We know all of those assumptions are wrong, but we have to simplify the model in order to run it and interpret it. And again, let me use the analogy of regression. What factor most affects the magnitude of the correlation, of multiple correlation? It's the variables we forgot to put into the equation. And there's no statistical test that could tell us you forgot an important variable. All we see is that r squared is lower than we thought, than we hoped. That's the same thing here. There's nothing Well, there are some tests we'll get into that may suggest draw a path between x2 and y1. It will tell us that will improve the model. But let me anticipate what I'm going to say. Do you follow the advice of the program? It all depends. Does it make theoretical sense? Theoretical sense. That's the most important criterion. Not the mathematics, not the model fit, it's your theoretical model.
So, I mean, the point would be if you can test a more complex model as far as you have a big number of observations.
That's right. That's right. Yeah. The more observations you have, the more complicated the model could be.
The less constraining parameters.
Yeah. Well, yes, but the more potential paths there could be, because you have more variables that could be connected or not. So more measured variables gives you more parameters to play with, but it also gives you more complicated relationships. Yes?
One last question.
I hope not. I hope there'll be many more.
I feel kind of guilty because I'm the only one that is making questions. But what happens, let's say, these are only measures to individuals, but can you use, let's say, because in multi-level analysis, there are correlation between data, let's say, from individuals from different clusters. So then you have different variances, and individual variances, you have to add that to the variance added by the correlation within the clusters. So to build a theoretical model like this, you have to obviously not to use data that are correlated, because then it will mess everything up, because you cannot assume that the variance are equals. Am I right?
Yes.
Okay. Yeah, then I understood it.
Yeah.
Okay.
This is not like hierarchical linear models. You cannot take clustering into account.
Okay, so we have this to dismiss clustering.
That's right. That's right.
Okay. Thank you.
Okay.
You're going to have next, last question again.
Okay, so all of these steps in terms of constraining parameters are necessary, but they may not be sufficient, because when you get into complicated models like the one I showed, and even the one I showed is simple compared to some other models, it's very difficult to calculate the number of parameters that you have to estimate. Also, the rank of the matrix may be less than the number of variables, and we don't know it. So we start off by constraining variables that we think should be constrained. Then we run the model, and the program will tell us how many more parameters we have to constrain. We always make a mistake with the first guess. Okay. Again, this is the second time. Second out of 715 times that I will mention it. Structural equation modeling is for testing theory, not for building theory. The constraints that we impose on a model have to be dictated by our theory, or by knowledge, or by previous results. Don't do it haphazardly. Okay so far?
Very good.
Okay, so now we're ready to actually run the model, estimate the parameters. And there are many different approaches. This is because there are different types of data, and there isn't one best method. If there were a best estimation method, that's what everybody would use. The fact, as with many parts of structural equation modeling or any multivariable technique, the fact that there are many different alternatives means that not one of them is the best one. They all have problems. Unweighted least squares has the major advantage that it's not making any assumptions about the underlying distribution. Don't have to assume multivariate normality. But it's scale dependent. If we were to measure depression with one scale and then change the scale to a different depression inventory, the results will change completely. If we were to score that scale differently, score each item -5 to +5 instead of 0 to 11, the results will change completely. This is a very undesirable property of an estimation technique. So almost nobody uses unweighted least squares. Weighted least squares is also distribution free, but it requires a very large sample size. It's asymptotically distribution free. What's large? Nobody knows. Large is probably twice as many subjects as you have. No matter how many you have, it wants twice as many. Weighted least squares with diagonal weight matrix. It's meant for ordinal data, which is great because almost always the data that we have are ordinal, not normally distributed. Does anybody use M+? No. No? That's unfortunate, because M+ is probably the most powerful program for running analyses like this. The most powerful, the most difficult to learn. Very steep learning curve. The advantage is, for the first year, you dial a phone and one of the two authors of the program, Brent Muten or his wife, I forget her name, Muten, will pick up the phone and answer the question for you. When it's available, it's very powerful. It's available on M+, not on other technique, not on other programs. And also, it doesn't give Ikaki's information criterion or the Bayesian information criterion, so you can't compare models. Maximum likelihood is the default in most situations, but it requires multivariate normality. And if the data are skewed or the data are ordinal, it'll give you results, but not clear how much to trust the results. And it may underestimate the model fit and the standard errors and inflate the goodness of fit chi-squared. Anybody still use SAS?
No.
Nobody. Forget about Prelis. Excuse me?
Too expensive.
Too expensive, yes. It's like SPSS, and it's falling behind programs like M+ and Stata. A new variation of maximum likelihood is robust maximum likelihood, which has robust estimators of the standard error and chi-square. So it assumes the variables are continuous, but not necessarily normal. So for programs that have robust maximum likelihood, that's what people tend to use. And then Bayesian, about which I know absolutely nothing, except that Bayes is dead.
Yeah, of course.
Yeah. And it has limited availability. Okay?
Just 1 second.
Yeah.
Mauro, ¿puedes colocar acá en el... Sí. Escribe SEM para buscar arriba en la página para buscar ahí. Ya, escúchame, escribe. Yo tengo teclado. Sí. Okay. SEM in Stata. Let's see the procedure they have in Stata.
Oh, which, yeah.
El segundo, ese. Okay. You don't have to order it.
No. No.
Dale. Classes of model for linear decision. You see what this is. Dale, basta. Do you see anything?
No.
Coming?
No.
Más?
No. Doesn't say. But it does say it allows for a lot of different types of data.
Okay.
So
or even ordinal.
Even ordinal, that's right. Yeah. Okay. So maximum likelihood for missing values, so FIML, which is quite good, and asymptotic distribution free, which likely means it needs a large sample size. Okay. If it says it's asymptotic distribution free. And then go up a little bit more. No, that's generalized SEM. Yeah. It gives you robust estimators of fit, which we'll get to in a little bit, okay. Which is also a very, very good feature.
Okay.
Okay.
Question.
Yes.
Is it good time for coffee break?
Always.
Yeah. Coffee break. Okay. Let's go for coffee break. Yes, all the way.
¿Está bueno el precio? Ya. Quiero café después de todo esto. Que eso yo no entiendo, hay cuestiones como técnicas del modelo, pero si yo entiendo la idea, y la idea es que uno asume demasiadas cuestiones. Hay como muchas cosas que se están desestimando.
No, lo que pasa es que
Mauro.
No, tú me dijiste, ya puedo realizar.
Mauro.
Estudia la dieta.
Sí,
Sí,
Okay, so we have specified the model. Yeah.
¿Alguna pregunta sobre la primera parte de la mañana? Entre que llegaron acá y fuimos al café, antes de eso no se puede responder nada. ¿No?
Okay. Now, let's see how good the model actually is. There are many different fit indices, and as with estimation techniques, there are many fit indices because none is ideal. One fit index is the chi-squared goodness of fit. And about the only reason that it still exists is that it's the only test of the goodness of fit that has a statistic associated with it, chi-squared statistic. So first, chi-squared goodness of fit should be not significant. Secondly, ideally, chi-squared goodness of fit divided by the degrees of freedom should be less than 2. Problems with chi-squared goodness of fit, as with any chi-squared test, is that it's very sensitive to the sample size. If there are fewer than 75 subjects, chi-squared goodness of fit is rarely significant. So even if the model is terrible, if there are few subjects, there isn't enough power to test it. On the other hand, if there are more than 400 subjects, chi-squared goodness of fit is always significant. And even if the model deviates only a small amount from the data, chi-squared goodness of fit will be significant if there are a lot of subjects.
May I ask something?
Sure.
You can keep the mic.
Me bajo, Vivi. So, what is the null hypothesis in the chi-square goodness of fit?
What is the
null hypothesis that
the null
should be
hypothesis?
tested?
Okay. The null hypothesis. See, in a regular goodness of fit chi-squared, Pearson goodness of fit chi-squared, the null hypothesis is that nothing is going on. We want to reject that. So that's why we're looking for a large chi-squared. In a goodness of fit chi-squared, the null hypothesis is the model. So we want to test the difference between the model and the data. And we hope there's no difference. That's why we want chi-square goodness of fit to be non-significant and small. Okay?
So if they shouldn't be the same, they should be different.
They should be the same.
La hipótesis de nulidad es que los datos ajustan el modelo. Por lo tanto, no la quieren rechazar.
Okay.
Yeah. The other problem with the goodness of fit chi-squared is that it's very sensitive to the data being non-normal, and especially to kurtosis. Everyone know what kurtosis is? No? Yes? Okay.
Tiene que ver con la forma de la distribución, ¿no es cierto? Más plana o muy aguda.
It's sensitive to the complexity of the model, and it's affected by the correlation. The magnitude of the correlations. If there are very large correlations, you get a poor fit. So it's not a great test, but everybody uses it. The other fit statistics, there are 3 different types: incremental or relative fit, absolute fit, and comparative fit. Incremental fit statistics are analogous to R² in multiple regression. 0 is the worst possible model, nothing is going on. 1 is the best possible model. The worst model is usually the null model, that the variables have variation, but there's no correlation among the variables. And the general form of all incremental fit indices, some variation on this. The worst possible model minus my model divided by the difference between the worst and the best possible model. And ideally, the value should be above 0.9, and we hope above 0.95. Yes?
Again, sorry.
Yeah,
So
good.
What is an example of the null model? It's the model between, because usually the null model is the model without covariables.
It's the model without covariances among the variables. None of the variables are correlated.
Yeah, but in this, let's say the example that you gave with intelligence or IQ, or which variables shall be included in the null model?
They're all, whatever model you specify. So if we go back to that very complicated model where I had 3 measurement models on the left, a measurement model on the right, a model combining all of the 4 latent variables, that's my model.
Y el nulo sería que no tenga correlación entre nada, que nada hace correlación. Ese es el nulo.
You still look confused.
Yeah, because usually the null model, in regressions, the null model is the model with the outcome by itself.
That's right.
Yeah.
That's right. But what does that null model mean? It means that there's no correlation between any of the predictor variables and the outcome.
Mm-hmm.
That's why it's the dependent variable by itself.
And also you can see intra-class correlation. Yeah, somehow.
Yeah. But the null model is saying there's no relationship among any of the variables. So if we go back, if we go back, the null model is that there's no relationship among these variables with symptoms. There's no relationship among these variables with wealth. No relationship among these variables with IQ. No relationship between these variables and well-being. And no relationship among the latent variables. Nothing is correlated with anything else.
You introduce that with the commands.
No, you don't have to. That's what it's assuming. When it's looking at the null model, it's saying, let's assume nothing is correlated.
Okay.
That's what the computer does.
And then your own model,
This is my model. My model is that these should be correlated.
Okay.
That these should be correlated, and so on.
Thank you very much.
So let's say we drop wealth from our model. The null model is still the same. It wouldn't change the null model at all because it started off by assuming there's no relationship. What it will change is our model. Okay. The normed fit index was the first fit index in the literature. Problem is, as you know from regression, every variable that you add to a multiple regression, except in the case of suppressive variables, which we don't talk about, but every variable increases the fit, increases R squared, even if it's a tiny amount. If you put in variable measuring eye color or height, even if the correlation with the dependent variable has a correlation of 0.001, it will increase R squared. There will be no penalty for putting it in. Okay. The normed fit index is the same. The more variables you put in, the higher the index, and that's not good. The comparative fit index is one of the most widely used. And it's the least affected by sample size. So that's why we use it. The normed fit index 2 is like adjusted R squared. Adjusted R squared penalizes you for the complexity of the model. So if you excuse me. So if you add a variable in multiple regression, it will increase R squared, but it may decrease the adjusted R squared. It's what's called a parsimony adjusted index. Keep it simple. This is the same. It penalizes you for a very complex model. So it's widely used. And the Tucker-Lewis, the NFI or TLI, is probably the most widely used incremental fit index. And again, you're penalized for adding variables into the model. Absolute fit indexes, there are two of them. The main is called Ramsey. Root mean squared error of approximation. Ramsey. And it's how well, in an absolute sense, the model fits. So it's a discrepancy. So ideally, it should, whoops, wrong button, should be below 0.05. If it's above 0.08, usually we throw out the model. We say the model fit is terrible. Between 0.05, 0.08, we say the model fits, but it's not great. We're looking for less than 0.05. A more recent fit, absolute fit, is the standardized root mean square residual. So it's the standardized difference between the observed and the predicted variances and covariances. And as with Ramsey, it should be below 0.08 and ideally below 0.05. AIC is useless by itself. We get a number, it doesn't mean anything. We use AIC only if we're comparing two different models and we want to see which model fits the data better. So we look for the lowest value of AIC. And a variant of AIC is BIC, the Bayesian information criterion. Again, useless by itself, good for comparing models. The lower is the better. Okay? And again, there are no statistical tests. You subtract one from the other, and there are rules of thumb about how much difference is good. But there are no statistical tests to say it's a significantly better model. Okay, so all incremental fit indices should be above 0.9, the Tucker-Lewis, the NFI, and so on. Ideally over 0.95. The absolute fit indices, Ramsey, and the root mean square should be below 0.08 and ideally below 0.05. Chi-squared should be non-significant, and chi-squared divided by degrees of freedom should be less than 2.
Is there any concordance among them?
If it's a very good model, they'll all agree. If it's on the edge, then it's quite possible that some of the comparative fit indices will be above 0.9 or 0.95, but Ramsey will be below or be above 0.08 and vice versa. Which do you trust? Depends how desperate you are for a publication. But my experience has been for good models, they all say the same thing. Or for bad models, it's those in the middle where you get differences. Okay. The respecification says that you have run the model, you've looked at the fit indices, you decide that the model has to be improved. How should you improve it? How do we get a better fit? The problem is, as with multiple regression, as I said, what most affects a multiple regression? The variables you forgot to put into the equation. Same thing here. The thing that most makes for a bad model is you forgot to put some important variables into the model. And there is no test for an omitted variable. The only way you could tell that you've omitted an important variable is by presenting your model in public and someone points and says, "Idiot, you forgot to measure this." That's the only statistical test there is. The only tests are for unnecessary variables and paths that may not be necessary, or some paths that may actually improve the model. The first thing you should do when you're evaluating the model is look at the paths. Of course, the sign should be in the correct direction. If you're hypothesizing a positive relationship and you come up with a negative path coefficient, you have problems. All path coefficients are parameters, so they all have a statistical test. Are the tests significant? The Lagrange multiplier tests tell you how much the model will be increased, will be improved, if we free some parameters. Some of the parameters that we fixed, we actually say they're free to vary. And the wall statistic is just the opposite. What is the effect of dropping parameters entirely? Again, as I said, I'm going to keep on repeating it. Whether or not to free a parameter, or to drop or keep one, or to drop or keep a covariance term, must be based on theory. If the wall statistic and the Lagrange modification index tell you to change the model, but it doesn't make theoretical sense, don't do it. You will get a better model, but it won't make sense and probably won't replicate. Okay, finally, let's get to confirmatory factor analysis, which, as I said, is one step in structural equation modeling, but is probably the most important step because it also stands on its own. We can do confirmatory factor analysis without doing structural equation modeling. Okay.
Any preference on a specific journal? Because sometimes some journals like one type of procedure and another, no?
No, journals shouldn't prefer one over the other. Which one you use should be dictated by the question you're asking.
Okay.
Yeah. Most of the measurement journals, assessment, personality assessment, Journal of Personality Assessment, you should use both of them depending on the question. Okay, exploratory factor analysis is driven by data. We just put the data into the computer, close our eyes, and hit the compute button. Whereas confirmatory factor analysis is driven by your theory. What do you think the relationship should be among the variables?
Yeah. Yes. But most of the time people like to validate a model which was built, let's say, in China.
Mm-hmm.
So that the model has mainly, let's say, 3 factors and
yep.
Factor log and so on
right.
and so forth. So, and most of the people like to test for if the model fits here in Chile.
Right.
Is that a good question or?
It's an excellent question.
Okay, but then, what if finally the model doesn't fit? You can use this procedure you were mentioning before about improving the model by.
Yeah.
But the result, what's going to be the result? Is the modify scale or so on and so forth? Wow.
You're asking a question that could be a course in itself. If I am testing, let's take it more realistic. I've translated a scale from English into Spanish, and I want to see if the scales are the same. We'll discuss it later. I have a model. I have a model that was developed in the United States. The American authors said there are 3 factors, and these are the items that load on each factor. In that case, I have a theory. So I should start off with a confirmatory factor analysis. Does my Spanish version correspond to the English version? If it does, and we'll discuss the different steps, beautiful. If it doesn't, then where do you go? And very often what we do is to say, let's stop right here. Last week in Concepcion, I was talking to someone. They took an American scale, and the American author said it has 2 subscales. They ran a confirmatory factor analysis, and the model didn't fit at all. So then they went back and said, okay, what do the data look like? Now we have no theory. So let's look at the data. So then they did an exploratory factor analysis.
So, and for the paper, you have to tell that.
Yes. And I said, this is how you should write the paper. We did a confirmatory factor analysis. These are the results. Results are terrible. We did an exploratory factor analysis. This is what we found. Period.
Okay.
In an exploratory factor analysis, there are no constraints. As we'll see, we do put constraints on in a confirmatory factor analysis. Minor point, we begin with correlation matrix. In exploratory factor analysis, we begin with the variance-covariance matrix in confirmatory factor analysis. And that's because we want to keep the intercept. When we start off with a correlation matrix, we set all of the intercepts to be 0. Here we want to know what the intercepts are. We don't get an unstandardized solution. We only get the standardized solution in exploratory factor analysis. All of the factor loadings are standardized, based on the standardized variables. In confirmatory, we get both. In exploratory factor analysis, we get factor rotation. We don't in confirmatory factor analysis because we say that there's only one factor or that the factors are totally uncorrelated or whatever. We specify the model. We don't rotate. We get factor scores in exploratory factor analysis. We don't. They're meaningless. In confirmatory factor analysis, there's no test of the fit in exploratory factor analysis. We get the same fit statistics that we do with structural equation modeling in confirmatory factor analysis, including a goodness of fit. We don't get it in exploratory, we do in confirmatory. Okay? Both forms of factor analysis are the same in that we are trying to discover a smaller set of factors that explains, that represents a larger number of variables. Those variables could be items on a scale, or they could be separate scales. Confirmatory factor analysis, as the name implies, is used to confirm a theory. Our theory of what the relationship is among those variables. In exploratory factor analysis, we achieve what's called simple structure. That is, a structure that's easy to understand by rotating the factors. In confirmatory factor analysis, we achieve simple structure by not specifying paths. Because in confirmatory factor analysis, we say that a variable is on factor 1 or on factor 2, not on both. Whereas in exploratory factor analysis, it could be on both. So the factor loadings tend to be higher in confirmatory factor analysis than exploratory. We're forcing all of the variance into one factor, rather than allowing it to spread out over all the factors. Is that clear? Okay. Let's do a confirmatory factor analysis. Let's assume I have 7 measured variables. I'll call them A1 through A7. And I'm hypothesizing 2 latent variables, 2 latent factors, F1 and F2. And I'm specifying ahead of time that variables 1 through 4 go with the first factor, 5 through 7 go with the second factor, and I'm assuming that factor 1 and factor 2 are correlated with one another. So that's the model that I'm proposing. Okay? So, notice that in exploratory factor analysis, there would be paths from factor 1 to these variables and factor 2 to those variables. I hope they are small, but there's no way I can specify that in exploratory factor analysis. Here I specify that there is no relationship between factor 1 and those 3 variables, or between factor 2 and those 4 variables, because I didn't draw any paths. Is that clear? Okay. So, let's assume this is what I find. The path coefficients these are standardized regression weights.
There is no one on there now.
No. That's why it didn't matter which variable we put the 1 on. These are the same as factor loadings in factor analysis. Okay? And we could get the squared multiple correlations or the communalities for each of the variables. Excuse me?
1 back. 0.04 is very low.
Very low, and also look at the path coefficient. Yeah.
It doesn't mean anything.
Doesn't. We'll get to it. Yeah. And even though I hypothesize the covariance between the factors, in reality, it's very small. So, this is my complete output. Okay? Does the model fit? Well, how many observations? I have 7 measured variables. Therefore, 7 times 8 divided by 2, I have 28 observations. Okay? Doesn't matter how many people. The observations has to do with the number of measured variables.
Why don't they put another name? Observation don't make confusing people.
That's right. It's to keep you confused.
Good.
Yeah. So then you have to pay people like me a lot of money to interpret. Otherwise, you could do it yourself. We can't have that. How many parameters do we have? Well, we have 5 regression weights, because don't forget, there was one that was fixed for each factor, right? So we only have to estimate 5 out of the 7. There's a covariance between F1 and F2 we want to estimate. 7 variances of the disturbance terms, and 2 variances of the latent variables. So that's 15 parameters that we want to estimate. We have 28 observations, so we're fine. We have a lot fewer parameters to estimate than observations. So in essence, we have 13 degrees of freedom. Okay, so does the model fit? My chi-square goodness of fit, 16 with 13 degrees of freedom. So, first chi-squared goodness of fit is less than 2. Divided by the degrees of freedom is less than 2. And it's not significant. So far, so good. These are my unstandardized estimates of the path coefficients. And as you could see, being a parameter, the estimated ones all have standard errors, so I could get a critical ratio, like a z-test. Does the model fit? Well, GFI looks good. The adjusted goodness of fit index, low, but it's still above the criterion. And the normed fit index is good. So, first of all, we were wrong about one variable. We thought variable A4 loaded on factor 1. Path coefficient is very low, and the R squared is low. Okay. If we had done an exploratory factor analysis, it could have told us, no, variable A4 doesn't belong on factor 1, it belongs on factor 2, or it doesn't belong on either factor. Confirmatory factor analysis doesn't tell us that. It only tells us, does our model fit? We were also wrong. We hypothesized that the 2 factors would be correlated, and we found that they're not. So it's telling us that the model as a whole fits, even though some specific aspects of the model don't hold. Okay?
Re-specification, right?
Re-specification. So do we change the model? So we have modification index. And the modification index tells us how much the goodness of fit will change if we follow the recommendation. So it's saying there should be a covariance between the disturbance term of D2 and the disturbance term of D6. And that will change the chi-square goodness of fit quite a bit. Does it make sense? Absolutely not. If I'm hypothesizing that factor 1 and factor 2 are separate factors, then it doesn't make sense to draw a covariance between an item from one factor and an item from the other factor. So this is one indication that the modification indices are totally atheoretical. And you should not follow them, no matter how much they improve the model, if they do not make sense. It's also telling us that maybe D3 belongs on factor 2 rather than factor 1. Again, look at the items, look at the factors. Does this make sense? If not, ignore it. Okay, let's forget about the regression weights. We rarely use them. Okay, so let's run a full structural equation model. This is the model we hypothesized ahead of time. This is our input. And this is what we find. So what is this telling us? This measurement model looks very good. Path coefficients are high. The R-squareds are good. This measurement model looks good. This measurement model looks good. And this measurement model looks good. So each of the measurement models looks very good. In terms of the structural model, symptoms is negatively correlated with well-being. Good. That makes theoretical sense. Wealth is not at all associated with well-being. So I may want to rethink the model, because here I am making the whole model much more complicated, measuring quite a large number of parameters, and in fact, wealth has nothing to do with well-being. And intelligence is positively correlated. You could tell I designed the model, being a bright, poor academic with no symptoms. Okay? So, number of observations is 66, based on all of the measured variables. Number of parameters is 23, so we have plenty of degrees of freedom. Nothing to worry about there. Chi-square goodness of fit divided by the degrees of freedom is low, but it's significant. So I would have to go back and take a look. How many subjects do I have? Is it caused by the fact that I've just got a lot of subjects, which would make it significant? Is it due to the fact that that's a fairly complex model, and that's a bad fit? So this is good, this is bad. GFI is low but acceptable. The normed fit index, which I really like, is good but just squeaking above the line. The adjusted goodness of fit index is below the criterion. Okay? So what do I do? Based on this, I would publish it with this model. I would also take out wealth, rerun the model, and it would probably be a good fit. So my paper would say, this is the model. It was poorly specified with respect to wealth. If I respecify it, this is what I find. Okay?
In some sense, you are doing exploratory then.
In some sense. Exploratory in terms of the model. Yeah. Okay, let's look at different confirmatory factor analysis models. This is the simplest model there is, despite all the Greek symbols. There's one factor, loads on 4 variables. So, like a Beck depression inventory, a scale measuring a single dimension. Okay. This would be 2 subscales that are not correlated with one another. So those of you familiar with the Minnesota multiphasic personality inventory consists of a number of scales that are correlated to varying degrees. But we wouldn't expect the scale measuring physical symptoms to be correlated with the scale measuring paranoid ideation. So we have 2 uncorrelated scales or subscales, each of them with a number of items. Another variation of this is when the 2 subscales are part of a larger scale. So for example, if I were developing a scale of anxiety, I may hypothesize that anxiety has 4 different components. An affective component, a behavioral component, a cognitive component, a physiological component. Each of those is a subscale, but they could all be put together as one overall anxiety scale. Is that clear? What's coming into more and more popularity these days is what's called a bifactor scale. And the difference between a bifactor scale and a higher order scale is a bit subtle. In a bifactor model, we're hypothesizing 2 or more separate factors. And we're saying they're not necessarily correlated with one another. So this, for example, could be the vocabulary subscale of an intelligence test, and this could be block design. So there's no reason to suppose that vocabulary and block design are correlated with one another. Vocabulary has a number of items, and block design has a number of items. But we also hypothesize that there's a general factor that affects all of the items. So how many people here are psychologists and have studied the history of intelligence? None? Okay. In the early days of trying to measure intelligence, one theory, which still is quite popular, is that there are 2 aspects of intelligence. There's a general factor and specific factors. So that if this is vocabulary, and these are the items, then vocabulary as a skill, as an ability, affects each of these items and doesn't affect these individual items with, let's say, picture arrangement, another subscale. But there's a global thing called intelligence that affects everything that we do. our math skills, our vocabulary, picture arrangement, comprehension about the world, knowledge about the world. So this general factor affects each of the items individually, and each of the items is also affected by its specific skill. Okay? Which is slightly different from this model, which is saying that these two skills are part of a super skill. This model is being used also to examine if I develop a scale that has subscales, do the subscales tell me anything over and above the total score? Do I really need the subscales? Are they really giving me useful information? And someone called Stephen Reese, R-I-E-S-E, done a lot of work with bifactor scales. And his conclusion is that in the vast majority of cases, the subscales don't add any useful information. Now, whatever we get from the total score, that's sufficient. Okay, it's the end of confirmatory factor analysis as an introduction, and it's almost 12 o'clock. Your decision. Do we want to continue how we develop a test, especially a translated version, or do we want to stop? How many say, let's go on? Okay, he's the majority. Okay. This is of most interest to people who are developing or translating scales into Spanish. Anybody doing that? Yeah, most of you. Okay. Let's talk about a little bit about measurement theory. When we talk about the items that comprise a scale, there are three levels of what we call item equivalence. The lowest level is when we have what is called a congeneric scale. I have no idea if that can be translated into Spanish. In a congeneric scale, all of the items measure the same construct, as we would hope. If we're developing a scale of depression or anxiety, all of the items measure depression or anxiety. But the size of the factor loadings can vary from one item to the next. So if we did a factor analysis on that scale, exploratory factor analysis, the factor loadings for one item may be very high and for another item very low. The amount of measurement error in each item could vary quite a bit from one item to the next. The variances of the items are uncorrelated. That's the standard assumption. Okay. If a scale meets only the assumptions of a congeneric scale, then strictly speaking, we cannot add up the items and come up with a total score. Because adding up the items assumes that all of the items are contributing equally to the total. This is saying they're not. Because the factor loadings are different, because the variances are different, each of the items is contributing differently to the total score. So strictly speaking, we should not be able to add up the items and come up with a total. But it's done all the time. Strictly speaking, we should not calculate Cronbach's alpha for internal validity, because each of the items is contributing a different amount of variance. So, in this model, the factor loadings are different for each of the factors, and the disturbance terms, the errors, are different. Is that clear? One level up from congeneric is a tau equivalent scale. Again, all of the items measure the same construct. That's a given. But now, all of the items have equivalent or similar factor loadings. They're all contributing the same amount to the total score. Although the measurement errors are still free to vary. Okay? This is the minimum requirement for adding up items and for Cronbach's alpha. So now the factor loadings are equivalent, but the disturbance terms, the variances, are different. And the highest form of scale is what we call parallel indicators. So the items measure the same construct, the factor loadings are equivalent, measurement errors are equivalent, residuals are uncorrelated. This is what we are looking for, ideally, when we're creating a scale. Okay? Any questions so far? So, this is what we are looking for. Okay. Let's talk about factorial invariance. Factorial invariance means that if we have different groups of people taking the same scale, same questionnaire, same test, that the different groups will be comparable in terms of the factor structure of the tests. Very often it's used to test whether males and females differ, whether a minority group differs from a majority group. The most widespread use of factorial invariance is to see if a translated version is the same as the original version. Okay. If you're going to do invariance testing, what you have to bear in mind is that we are dealing with the unstandardized solution to the confirmatory factor analysis. This is the one time that we are interested in the unstandardized solution. Most of the time, we just are interested in the standardized solution. This is the one time we're interested in the unstandardized solution. Secondly, the samples should be relatively equal in size. So if you are dealing with a test that was very widely used in the United States, very large sample size, you have a much smaller sample size here, you've got a problem. Unless you could get an estimate based on a smaller sample size in the US. Okay. What I'm going to discuss now are the steps that should be done in sequence. And if one step fails, then you stop. No sense going on. And also the invariance models are tested so we could test whether the next restriction produces a significantly different answer using the difference in chi-square test. Okay. We start off, yes?
What it means that the models are, can you go backwards one please? The invariance models are nested. What's the importance of that?
Do you know what the term nested means? Yeah. The importance is you could use a difference in chi-square test only if the models are nested. So only if one model is a subset of the other model.
Because then the data should be correlated.
That's right. That's right.
And you need no correlation here.
We're not so much interested in the correlation. We're interested in the fact that we start off with a model and we test that model. Then we put restrictions on that model. So that second model is a subset of the first model. It's the first model with restrictions. So it's nested under the first model. So we can look at how much the chi-square changes.
Okay.
And then the third model is the second model with more restrictions. So the third model is nested under the second model. Okay. What we do usually is, let's say we're translating a scale. We would start off with the exploratory factor analysis or a confirmatory factor analysis of the original scale, of the scale in English. Then we would say, are the pattern of the free parameters the same, of the fixed and the free parameters? That is, if I hypothesize that the original, the English version of the scale has, let's say, 3 factors. These items load on the first factor, these items load on the second factor, these items load on the third factor. Now I look at my Spanish version, and I'm asking the same thing. Do the same items load on the first factor, the second factor, and the third factor? I don't care if the factor loadings are the same. I'm not interested in the magnitude of the factor loadings. At this stage, when I'm looking for the configural invariance, I'm simply saying, are the items that load strongly on the first factor in the English version the same items that load strongly on the first factor in the Spanish version? Is that clear? No? You still seem to have questions. Let me go over this again if you're not clear, because if you don't get this, then nothing else will make sense. Let me see if I can find a model. Okay, let's take this model. Forget it. Oops. Okay. Forget about this. I'm saying, let's say that this is what I find, or what was reported in the literature with the English version. That there are 2 factors. These items load on the first factor. These items load on the second factor. At my first step, when I'm looking for configural invariance, I'm asking, in the Spanish version, do these 3 items load on the first factor? Do these 3 items load on the second factor? I'm not interested in the magnitude. I don't care whether these lambdas, the factor loadings, are the same level in English and Spanish. I just want to know, do they load on the same factor? I'm not interested in the variances. Again, all I want to know at the configural level is the configuration. That's why it's called configural. Is the configuration of items the same in both languages?
And by configuration, you mean A1, A2, A3 into the factor 1?
That's right. Okay. Exactly. Okay.
That was independent of the factor loading, right?
That's right. I don't care about the factor loading. All I care about is that there is a factor loading that's at least significant.
Oh, okay.
If I do not find configural equivalence, stop. There's no sense going on. If I do find configural invariance, then I impose some constraints with what's called a weak or a metric invariance. So it's the previous model, the configural invariance. Now I'm adding the constraint that the unstandardized factor loadings are proportionately equal. That at least they're in the same rank order. Okay? Any questions so far? If I find weak invariance, metric invariance, then I could go on to the next step, which is strong invariance or scalar invariance. So now I've met the requirements for metric invariance, and now I'm saying that the unstandardized factor loadings and the intercepts, that is the means of each of the items, and that's why we're dealing with unstandardized, by the way, solution, so I can get the means. In the standardized solution, they're all set equal to 0. But now I'm asking the question, are the unstandardized factor loadings and the means, the intercepts, proportionately equal? So it's not only the factor loadings, but also the means that I'm interested in.
What do you mean by proportionally equal? It may be different, the factor loading, but when you compare one to the other...
That's right. The rank ordering is the same. If I don't find this, stop. If I do find it, I go on to the last stage, which is strict factorial invariance.
You should stop at the previous level.
Yeah.
What should you do?
You should wait until I get to the right slide. Okay? So now I'm asking, are the unstandardized factor loadings, intercepts, and residual variances equal? If I find this, I could rejoice. 2 pisco sour. Yeah. Each item.
Okay.
Okay? This is if you reach this stage, you're fairly confident that the translated version and the original version are comparable.
No cheating on the data.
And no cheating of the data. That's right. That's right. Okay. So, how do we do it? What we're doing is a multiple group confirmatory factor analysis. We assess the model separately for each group.
What do you mean by group?
English and Spanish.
Okay.
Or males and females, or whatever. So for each group...
Yeah. Can you split the sample by random and then do this?
Why?
I don't know. Because you have to have two groups?
Yeah, but it's... The purpose of this is to see if the two groups are similar.
Okay.
If you start off with a similar group, I'm not sure what you're testing. So, for each group, does the model fit? Are all of the factor loadings large? If they are, go on to the configural model, and that's the baseline model. That's what you're starting off with. If the configural model fits, test for weak invariance. So are the factor loadings, in other words, the slopes, equal across group? This is just details we discussed before. Then we go on to weak metric invariance. So we fix the variances equal in both groups. Okay? And then if that fits, we test for invariance in the intercepts. That is the means of the items. Okay, this is just if you're using different programs. Okay. So the criteria for factor loadings with maximum likelihood or restricted maximum likelihood, the change in the CFI should be less than 0.01, change in Ramsey should be less than 0.015, change in MR should be less than 0.03. Was the criteria for moving from one stage to the next. And those are the criteria for the intercepts and the residuals. This won't be on the final exam. You don't have to memorize these numbers. Okay, so what happens if you don't find invariance? You may end up with what's called a partial invariance model. It's not completely invariant. So check the modification indices. See where the problem is. What paths aren't meeting the criteria. Tomorrow we'll discuss differential item functioning. So put this aside for now. But what it's doing is testing the equivalence of each individual item. And it may be necessary, if you find non-invariance, that you have to drop some items. That maybe some items are not translating well because the translation is poor, and also don't forget, translation is not a matter only of going between two different languages. It's going between two different cultures. And it may be that the item doesn't make sense in a different culture, even though the translation is good. So you may have to drop some items, which leads to a problem in that the translated version of the test is now different from the original version. But you have no choice. Okay. If you are reporting structural equation model, confirmatory factor analysis in an article What should you report? Sample size. When it comes to designing analyses of variance, t-tests, we have computer programs that could figure out sample size. You just put in the effect size, work backwards, it will tell you what sample size. When we get to multivariable techniques, there are no sample size calculation programs. That's even worse with structural equation modeling. I've read a number of articles in multiple regression, in factor analysis, in structural equation modeling that says, forget all these rules of thumb. There are exact methods. As long as you know what the factor structure is, how strong it is, in factor analysis, how many factors there are, what the communalities are, you could calculate the sample size. And I say that's ridiculous. Because if you had all that information, you wouldn't be running the test to begin with. You run the test to find out that information. So suggestions like that are like epidemiologists. They give you an answer, but everybody knows the answer already. So it's useless. So what we have are rules of thumb. Whoops. Some say you need a minimum of 200 subjects. Doesn't matter how complex the model is, you have to have at least 200 subjects. Some say that the ratio of the sample size to the number of variables should be 10:1. Others say that doesn't make sense because each variable could have up to 3 parameters. You have the path coefficient, the variance, and the disturbance. So there should be a sample size per parameter rather than per variable. If you use M+, you could actually do Monte Carlo simulations. And Muten and Muten outline how you can use Monte Carlo to decide on a sample size. Most people don't do that. Most people just say about 10 subjects per parameter. If you do a t-test, an analysis of variance, or regression, you don't have to report what software you used. I know a lot of journals insist on it. I think it's stupid. It's like asking you to say whether you used a pencil or a pen to record the data. All the programs give the same answer, except Excel, by the way. Don't use Excel for statistics. Things are very different with structural equation modeling and confirmatory factor analysis. Each of the programs uses a different approach, makes different assumptions. So you have to say which program you used. And some of the older ones, like Amos, are limited. They don't give you the number of choices, the number of options, especially for estimation, that the newer programs do. Does anybody still use Amos?
No.
No, because nobody uses SPSS. Yeah. Again, M+ is probably the best. Stata is probably a good second. Anybody use R? Nobody uses R? It's free.
That's the reason why.
The advantage of R is that it's free and anybody could write programs for it. The disadvantage of R is that it's free and anybody could write programs.
But very few anybody.
What it's missing What R is missing is a good front end so that people could use it with the same degree of ease that they use SPSS or STATA. Until then, it's difficult, but look into it. It's very powerful, does lots of things, and it's free. I thought all graduate students used it. Okay. You have to state which estimation procedure you use and justify it. Not just, I used this because it was available, but I used this because my data were like that.
But most of the time we use ordinal scale, like
Yeah.
here and so on.
Yeah.
So,
Yeah. So be it. Yeah. If you're doing a factor analysis, did you extract the right number of factors? Anybody do factor analysis here? Huh? Use eigenvalue 1 as the criterion? Don't. Scree test? No. Should use parallel analysis. Yeah. To determine the number of factors. There are programs now available free on the web to do parallel analysis. And that's the gold standard. Most journals will not accept a factor analysis unless you also do a parallel analysis.
yeah, we submitted the paper and they just do parallel analysis.
Yeah, I probably reviewed it. If you change the model, justify the change that you made. Not only that the program told you to change it, but that it made theoretical sense to change it. If you're comparing models, use some statistic, change in chi-square or whatever, change in AIC or BIC, to justify that the models are significantly different.
But in confirmatory factorial analysis, you don't use a parallel analysis, just
No,
exploratory, right?
that's right. Yeah. Yeah. Okay. This is the 938th time I've said it. That these are model testing techniques, not model building techniques. I'll forget about causal model because I haven't talked about that. In terms of sample size, they are very hungry. They always need twice as many subjects as you have.
Regarding time, maybe 5 times.
Maybe 5 times, that's right. And they're probably very sensitive to assumptions about normality. So, they're very useful techniques, very powerful techniques, but you have to know what you're doing. Questions?
Thank you. Very good.
Questions?
Preguntas. Si la pueden hacer en castellano también.
Don't forget, it's all going to be on the final exam. You better understand it. Of course. Yeah, good. Good.
You usually refer to sample size, but for this kind of testing, does the sample need any specification? Because
I'm sorry, I didn't catch the end.
any specification, let's say, of course it's a random sample, but I usually see that.
Not necessarily.
Yeah, I want to ask you about that, because I usually see that psychologists do not pay attention to probability sampling issues, and I would like to know why. Because let's say if they use people from Universidad de la Frontera to test something, of course we are correlated, so that are correlated because intra-class correlation will be high. Why they do not take that into account?
It's not well. Many, many years ago, there was a statistician named Quinn McNamara, and he defined psychology as the study of the college student.
What?
The study of the college student. Because everybody tested college students. Why? Because they're available.
Yes.
Because in many universities, students have to take part in a certain number of studies. My own bias is, if I'm reviewing an article about a clinical scale and they were testing it on a college sample, I'll reject it. Because you can't test the clinical scale on a college sample, a university sample. But it's not only psychologists. If you were doing a study, where would you get your patients from?
It depends on the research question.
Okay, tell me about a question you're interested in.
Okay, what's the association between educational level and obesity?
Okay, where would you get your patients from?
From the general population.
That's unusual. If you do a study in hospital, you get patients from one hospital.
Yes.
Yeah? I don't get a random sample of all patients in all hospitals in Canada. It would be impossible. I use my hospital. Why? Because it's convenient. Because everybody knows me.
Yeah, I know.
Because everybody owes me favors.
To account then the generalizability of the results.
People don't. They assume that patients at McMaster Hospital, where I work, are representative of patients in all hospitals. And we know that's wrong.
Very wrong.
Very wrong. First of all, it's a quaternary care teaching hospital. We get referrals from other teaching hospitals. So what patients come to McMaster? Patients who are the sickest, the most difficult to handle, but not too sick. Because if they're too sick, they may die in the helicopter ride from their hospital to McMaster. Yeah? So the very, very sickest, yeah, die in their own hospital. So we get very sick patients, but not the extreme sick. We get patients who are the most interesting, because we have people who specialize in different disorders. So we know our hospital may be representative of other tertiary care or quaternary care hospitals. It's not representative of all hospitals. But where does medical research take place? It's always in tertiary care hospitals. Because the only people doing medical research, for the most part, are people in medical schools. You don't have physicians in the community doing research.
Yeah, some.
Oh, very few. Look at a journal. Look at a journal. Look at whom to write for reprints. And you know, at the very bottom of the first page, and in almost every case, it's going to be at a university and a university teaching hospital. Yeah.
Yeah, but I still don't get the answer, because my problem is that I've been asked sometimes to review grants from psychologists, and it calls my attention because I'm the picky one that pays attention to biases.
Mm-hmm.
For me,
good.
Are biased.
Good.
Because they, for example, sometimes I was asked, they were trying to test an intervention,
Yep.
but they were taking only people that went to certain
primary care centers.
But you
and
have.
say for elderly, I say no, because you are leaving out all the elderly that do not attend to tertiary care centers that are at home, that if you are going to generalize, you should take them into account. So my question is more general in the sense that I'm just curious about the fact that why not taking the sample characteristics into account, because another teacher that I had told me that
him, forget it. Okay. He's wrong.
But it's according to,
no,
we develop community studies in the population, and of course, if we do not select correctly the sample, we can have the whole study bias.
Absolutely, absolutely. But you have to consider first a number of things. First, it's not just psychology. I'd say it's everybody. Second, in many cases, it's not possible because of logistics, because of pragmatic concerns to get a general sample. Let me give you an example. We just finished a 7-year study involving 2,300 homeless mentally ill patients. Were they a representative sample of all homeless mentally ill?
No, probably you're in city or you're in area.
We used 5 different cities across Canada.
Oh, then
well, yes and no. We used Moncton, which is a very small city. We used Montreal, which is a francophone city. Toronto, which is the center of the universe. Winnipeg, which is in the middle of the prairies, and Vancouver, where everybody is stoned. High on drugs. You could argue even those places are not representative because we didn't hit small rural communities. They were all, by definition, cities that had teaching teaching universities, because everybody associated with the study was an academic. When we finally did the sampling, we told the social workers, enroll patients or people who come to your attention because they're homeless and mentally ill. We didn't get a representative sample because we got the people who were most likely to come to the attention of the social worker. So who are those? Those who are recently homeless, those who are most disturbed or very ill. So no matter what you do, you hope you could get a representative sample. You never do. The only time you could do it is if you're using a population-based sampling, and that's extremely expensive. The Canadian Community Health Survey, which we do it every 2 years, takes an entire year to do the sample. It's only the federal government that has the resources to do that.
No, I understand that part, but let's say what it doesn't make sense to me, if sampling is not so important, then why you dismiss variance? Because it doesn't make sense to me that if you didn't select a probability sample, then you are dismissing variance and not taking into account that the data might be correlated by nature.
You're right. Sin embargo.
However.
Why is it the first phrase I learned in Spanish? Because it's true. There are practical considerations. There's always pero, but. I have limited money. I have limited time. I have limited resources. If I'm doing a study of anxiety, I don't it would be very difficult for me to get the resources to do a nationwide survey.
No, I understand, but let's say, okay, let's suppose that I get the sample size enough.
Yeah.
So then, can I take into account, what I mean is that, are there any way to then take into account the variance? Because, of course, if you don't, there are practical reasons why you cannot reach the probability sample size. Okay, but then, are there any way to take into account variance?
Only if you know it. And you rarely do. I mean, samples, national samples, build in corrections for non-response. They build in corrections for sampling.
That's why sample size is so important then, because you need larger sample size.
Yeah, but you also have to know what those correction factors are. And if I'm doing a study in Hamilton, I don't know how my sample differs from Toronto, Vancouver.
Okay.
Yeah.
But in scale development, if you want to build scale, actually the sampling is related to having variability. You cannot have all people located into one end of the scale.
Wait till tomorrow.
Huh?
Wait till tomorrow. It's possible.
Because I think the question was related to that. You need to have variability. You cannot have all the same people together.
Yeah.
Okay.
Good.
Hasta mañana. Misma hora. Tal que se pueda.
Yeah.
I need to check my mail just for a minute.
Go ahead.
You want to go to my office? It's at the end.
Okay. Yeah. Yeah. Yeah.
Or otherwise, wait for me here.
I can wait
It's
for
up
you
to
here. I can wait for you here. Yeah.